Hey everybody, Dr. A here, and in this video we're going to be exploring a beam internal loading example. So let's go ahead and get started. Given here, we're being asked to determine the internal normal force, shear force, and bending moment at point B in the beam. So let's take a look at what we have here. We have what's called a simply supported beam. I'll make a note of that. This is called a simply supported beam. And the reason why it's called that is because at one end you have an external pin connection, and at the very opposite end you have an external roller connection. So anytime you have a beam segment where one of the ends is supported by a pin and the opposite end is supported by a roller, we call that a simply supported beam. All right. So we have this simply supported beam, and it's supporting a uniformly distributed load here of 200 PLF, and then it has a single point load here of 300 pounds, and we're being asked to determine these internal loads at this point B right here. All right, so the entire beam length is 10 feet, right? 2 plus 1 plus 7 is 10 feet, all right? Point A is the far left side, that's the external pin. And then the point that we're interested in determining the internal loads is point B, which is 2 feet away from point A. Now that 300 pounds is 3 feet away from point A. So this 300 pounds is 3 feet away from point A. And then point C is on the opposite side. All right. So how do we go about this? Well, if you watch the background video, let's write solution here. If you watch the background video before this, we use this technique called method of sections. So we're going to make a note here. We're going to say use method of sections, and we're going to pass a cut section through point B. All right. Now the video before this, the background video, says pass the cut section through the point of interest, right? So our directions tell us that we're interested in point B. Now before we get excited and we do it, we need to ask ourselves a couple of questions. The first question we need to ask ourselves is, okay, when we pass this cut section through point B here, which free body diagram do we want to analyze? So I'm going to ask that question here in orange, all right? Which free body diagram do we want to analyze? Okay, now, does it matter? Well, it doesn't. If you remember from the last video, you could analyze either the left side of the cut. All right, so we make this cut through B. You could look at this little piece here, or we could look at the right side of the cut. So we could use either free body diagram, either a left or a right free body diagram. So which one should we use? Well, my previous video, I stated that my rule of thumb is I typically analyze the free body diagram that is less complicated. So to me, looking at a left free body diagram when I do my method of sections is going to be less complicated. So I'm going to make a note here. I'm going to say, let's analyze a left free body diagram since it seems less complicated compared to the right free body diagram. All right, so that's the first question you want to ask yourself is which free body diagram do you want to analyze, and then answer that for yourself. Okay, so we're going to look at the left free body diagram in this example. The next question you want to ask yourself is, do we need to solve for any external reactions, right? So do we need to solve for any external reactions before using method of sections? Okay, so the way you answer that question is you look at what will be the free body diagram that you're going to analyze, which we said for this example we're going to analyze the left free body diagram, and you see if there are any externals that will show up there. Well, the answer to this question for this example is yes, we do need to solve for some externals before doing method of sections. We have to solve for the external reactions at A because those are going to be inside of that left free body diagram. So we're going to say yes, solve for the externals at point A, since those will be in the left free body diagram. Now, could we solve for the externals at point C? Sure, why not? I mean, you could solve for CY there if you wanted to, but we don't have to, since we have, for this problem, we have decided we're going to look at this left free body diagram, okay? So I'm going to start with first draw a free body diagram of the entire system to solve for AX and AY, all right? So the first thing I'm going to do is go through my process to solve for those externals AY and AX. Now, for the sake of completeness, I'm going to go ahead and draw CY here as well. And here is my uniformly distributed load. I think that was 200 PLF. And then we had 300 pounds here. And we have these dimension lines here, okay? So I'm gonna go ahead and I'm gonna get rolling on this. I'm gonna say sum of the moments about point C equals 0. Counterclockwise is positive. So I'm gonna be able to write negative AY times 10 feet plus 300 pounds times 7 feet. I'm gonna wrap this equation around here because I'm running out of room on the screen, plus 200 PLF times 10 feet, that's the length over which is distributed, and then times 5 feet, that's the moment arm, all equals 0. Do a little bit of rearranging, and I should get AY is 1,210 pounds reacting up, okay? Now, so that's an important number. I'm not done yet, but that's an important number. That's gonna I'm going to need that later. Now, what about AX? Well, nothing is applied in the X direction, so by observation, AX is 0. But if you ever want to just show that work, you can say sum of the forces in the X direction equals 0. And then clearly here, AX equals 0 because nothing else in this entire system free body diagram has an X component, okay? So all I've done now is solved for the externals I need to perform the method of sections process that I need to perform. So I'm going to now look at method of sections, and I'm going to say, let's look at a left free body diagram when cutting through point B. All right. And so when I do that, what's going to show up in that left free body diagram? Well, the AX that I just calculated is going to show up there, 1,210 pounds. And I'm going to exaggerate this a little bit. Here's that cut. And let's color coordinate a little bit. Yep, I used red here. So this will be point B. Okay. Now what's going to show up at point B? Well, I'm going to have a shear force VB. I'm going to have an internal bending moment MB, and I'm going to have an internal axial load NB, okay? Now, what about, am I done with this free body diagram? No. You got to show all of your known and unknown forces and dimension lines. So remember, we still know something here. We know that there is a uniformly distributed load over this little length. That's the 200 PLF, okay? That's there. That 200 PLF was spread out over the entire beam, and you're making this cut at point B, so a piece of that 200 PLF does have to show up on that free body diagram. If you don't include that, then that's incorrect, okay? And what is this dimension line? This is 2 feet, all right? Now, if you want to, you can go ahead and show that AX here is 0, but since it's 0, you don't have to show that if you don't want to, okay? So this is my method of sections, left free body diagram, and I'm going to apply my equilibrium equations. I'm going to say sum of the forces in the x direction equals 0. Clearly, the internal normal force in B is 0 because AX is 0, all right? What else? Well, I'm going to say sum of the forces in the y direction equals 0. And again, I'm looking at this free body diagram. I just move left to right, go very systematically here. We're going to say 1,210 pounds going up minus 200 PLF times 2 feet. I'm going to wrap the equation around because I'm running out of room. Minus V equals 0. Minus VB equals 0. And again, that VB is right here, all right? And then we say VB equals 810 pounds. Now, when we rearrange this equation and we solve for VB, it's going to come out positive, which means that it's in fact pointing in the direction that we assumed here in this method of sections free body diagram, okay? So it's 810 pounds pointing down. And then finally, my last equation is sum of the moments about the cut equals 0, counterclockwise positive. And I'm going to come down here. I'm going to say minus 1,210 pounds times 2 feet plus 200 PLF times 2 feet times 1 foot. And then plus MB, that's the internal load I'm looking for. So plus M sub B equals 0. Do a little bit of rearranging, and M sub B will be 2,020 pound-feet rotating counterclockwise. So it's gonna, when you rearrange this equation, MB will come out to be a positive number, which means that it is in fact rotating counterclockwise. So here's a couple of extra notes to be aware of when you go through this process, and don't forget, all right? Here's some notes. So we'll put a star here. We're going to say we're going to apply 3 2D rigid body equilibrium equations to the free body diagram when using method of sections, okay? So what that meant is when we looked at this free body diagram, when we were doing method of sections, notice we applied 3 of the rigid body diagram, rigid body equilibrium equations. Some of the forces in the x direction equals 0, some of the force in the y direction equals 0, some of the moments always about the point where you're making the cut equals 0. 3 equations, and we use those 3 equations to solve for these 3 unknown internal loads. So that's what you do every time you're doing method of sections on a beam. That's the first note we want to make. The second note we want to make is we want to always assume the unknown internal loads are pointing in their positive sense. What that means is make sure that when you do your cut section at the point of interest, when your internal loads become visible here, you point them in the typical positive sign convention. So if you remember from the previous video, positive shear at a cut causes the free body diagram to want to rotate clockwise. Positive internal bending moment causes the free body diagram to want to bend concave up, and positive internal normal force causes tension at the cut section. So if you're a little rusty on that, look back in your notes, go back to the previous video, because that's where I explain all of that information. All right. So in summary, I like to write a summary of my answers. N sub B equals 0. V sub B equaled 810 pounds, and that was pointing down on a left free body diagram. And M sub B is 20 pound-feet going counterclockwise on the left free body diagram. What would have happened if we looked at a right free body diagram? We would have gotten the same numerical answers, but the signs would be the opposite if we had analyzed the right free body diagram. Okay, so that concludes this video. If you found this helpful, please hit like and subscribe, and be on the lookout for other videos with similar content. Thanks for watching.